You remember we started the last lecture by remembering this formula for the null states of the reducible representations of the Cauchy determinant. Okay, HRS is equal to H0 plus 1 by 4 R alpha plus S alpha minus the whole thing square. Then where H0 was equal to 1 by 24 C minus 1 and alpha plus minus was equal to square root of 1 minus C plus minus square root of 25 minus C the whole divided by square root 24. Okay, then we continued in the next in the last lecture to describe this linear dilettante theory. So we looked at the theory with the action 1 by 8 pi del alpha phi plus what was it? Plus 2 gamma phi r, and then later we replaced gamma, went to I think square root 2 alpha. Yeah, I square root 2 alpha. Okay, so the action effectively was 1 by 8 pi integral del alpha phi plus 2 square root 2 I alpha r. Okay, you remember that we discussed that we got that this theory in flat space plus that one point at infinity had more or less the same correlation functions. Actually, the only part of it that's affected is the zero mode. The oscillators are unaffected. Okay, more or less the same correlation functions, but had a different conformal structure because we had a different stress tensor. And in particular, we found that C was equal to 1 minus 24 alpha square. Is that right? Okay, I'm going to use the notation of this book. So they use alpha naught. Okay, so alpha naught square. Okay, and we also reminded ourselves that the vertex operators e to the power I square root 2 alpha phi. Let me check I'm getting the normalization right. These vertex, yes, I square root 2 alpha phi. They turned out to have scaling dimension. H alpha was equal to, well, we would have got k square by 2. So there's alpha square, I think, and then plus or minus alpha naught. Minus 2 alpha naught. This you remember. Okay. And right at the end of the last lecture, we rewrote those relations for the Cauchy determinant, just trading C for alpha naught. Okay, and when we did that, we found, of course, the formula for HRS did not change, but the formula for H naught was now H naught, just by substituting this in here, was equal to alpha naught square. And alpha plus minus became square root of this became 1 minus, it was alpha naught plus square root of, alpha naught plus minus square root of 1 plus alpha naught square. Okay. H naught is minus alpha naught square. Correct. Minus alpha. Yeah, at least in general they are non-unitary. There may be specific places, in fact, there will be specific places where they're unitary. We'll get to that. But in general, these are non-unitary models. Okay, excellent. So now we're going to study, we're going to continue our study of this. So where are we going with this? Go on.
So, let's say we have two operators which are the same alpha. Are those?
What do you mean two operators which are the same alpha?
Sorry, same edge, same dimension.
Same dimension. Yes.
Scaling dimension. Is that how do you say that it's degenerate? Why do you consider those two operators as the same? Like when we were discussing earlier, you said that this different, like 1, 2 corresponds to 3, 5 RS.
Okay.
So here you have
yeah. Okay.
How do they correspond to the same operator?
Okay. In that discussion, you see, what we were doing was looking at fusion rules.
Yeah.
When we studied fusion rules, we asked what 3-point functions could appear. Now, 3-point functions were characterized by the h's of the operators. If you remember the logic, it was we wrote down 3-point functions, then we wrote down the differential equations coming from the null states, and asked for what values of h's are those differential equations satisfied. So for that question, if you have two different operators with the same h, you can't see the difference. Okay, so that question was purely a constraint on dimensions. So for that purpose, if you got 1, 2 as same as 3, 4, it was just a way of labeling dimensions. Okay, there was no other abstract notion of operator there. We just had, what dimensions could appear in the 3-point functions. Is this clear?
Yeah, but just simply because the weights are the same, why does it mean that?
Yeah, so what you are saying is that these are the set of dimensions that could appear. Now it could be that the theory will have two operators with the same dimension. Whether we called it 1, 2 or 3, 4 didn't matter. It could be that you could have degeneracies with the same dimension. Indeed, if we look at the free boson, that is the case, because e to the power ikx and e to the power minus ikx, both in the same dimension, yet they're different operators. Okay, that could happen. That is a matter, that is something that you have to study when you look at the theory. In that discussion, all we did was constrain what operators could appear. Now, as a matter of fact, in the simplest implementation of minimal models, and this we will see largely when we look at partition functions.
Because here also you can have two different alphas corresponding to the same edge.
We can have two different alphas corresponding to the same edge, and we're going to deal with that. But let us get to that. Okay? In the free boson, the example of that was ikx and minus ikx. Yeah. That's how you got two different alphas corresponding to the same edge. And indeed, they were distinct operators. One corresponded to a particle moving that way. One corresponded to a particle moving this way. So there's no general rule which says that two operators with the same edge are not distinct. Okay? However, yeah. Okay, let's see how we use that, how we use this stuff. So if we just took this theory by itself, not mutilate it the way we're going to in order to study the minimal models, then the two different alphas that you're talking about are distinct operators. Okay, there's no question about it. We can solve the theory. We can find its torus partition function, which in fact is the same as the torus partition function in the absence of this R, because that partition function doesn't see the R. Okay, the path integral that gives you the torus partition function, because the torus is flat, is the same path integral as for the free boson. Okay, and definitely you see two separate operators. Okay, but let's keep going as we come along. Okay, certainly there's no general rule that if you have two different operators of the same dimension, you should identify them. There's no general rule. Okay, yes, yes.
Here there is an operator which has dimension 0 also, is alpha equals to.
Here there is an operator that has dimension 0. It's different from identity. Yes, and this operator will genuinely be distinct from identity. Okay, it's only in a unitary theory that every operator of dimension 0 is the identity. Yeah. Okay, so these are weird theories because of the lack of unitarity. Okay, however, they'll prove very useful as we will see. Okay, fine, excellent questions all. Let's keep going. Okay, now how are we going to use this theory? You see, the idea was that we're going to try to explicitly construct the minimal models. So what we've managed to do is, we'll soon see where minimality comes in, but at least we've got some explicit construction of theories with central charge less than 1. If we choose alpha naught in an appropriate way, and I'll give you some sort of logic for that as we go along, we can get the central charge for the minimal models. So some explicit construction with the right central charge to be a minimal model. Okay? But it looks very different from a minimal model. Because minimal models were characterized by the fact that they had only a finite number of Virasoro primaries. However, in this model, we have an infinite number, in fact, a continuous infinity of Virasoro primaries, one for each alpha. Remember, del phi was no longer a Virasoro primary in this case. In the free boson, del phi and v alphas, for all alphas, were the set of Virasoro primaries. Here we just have the v alphas, but okay, you've removed 1 from a 1 plus continuous infinity, you've not changed it very much. Okay, it's a very large, this has the operator content of a C equals 1 theory, not of some C less than 1 theory, not like a minimal model, which has finite number of primaries. Okay? So what's the hope? Okay, we've got the right central charge, but we still seem pretty far from getting the physics that we really want. Okay? The hope is the following, and over perhaps this lecture, but most likely the next lecture, I will try to outline the mathematical basis for that hope. Okay? The hope is that one can perform some sort of reduction of this theory. Let me say in particular how it will work. What we will do is on the Hilbert space of this theory to identify an operator that squares to 0. Okay, this Hilbert space is the full Hilbert space ranging over all alphas. Okay, actually what we will do is look at a particular truncation, a closed truncation of this Hilbert space, but it will still involve an infinite number of alphas. We'll see this truncation in this lecture. Okay, and we will construct on that Hilbert space for appropriate values of the C naught, the values that are fit with the minimal models. Okay, what we will do is construct an operator that squares to 0. Okay, this operator we will then treat as a BRST operator. Every time you have an operator that squares to 0, okay, the problem of BRST cohomology associated with that operator gives you a closed subsector of the correlation functions of that theory. Okay, this is how it works in gauge theory. You've got some larger extended Hilbert space, but we can focus on the BRST cohomology and get correlation functions that, from the point of view of the path integral, are well defined. Okay.
So here you are talking about the unitary.
No, not necessarily. PP prime.
Okay, PP.
Yeah, remember unitarity was PP plus 1. Okay, in general we will do it for the PP prime thing.
So even in a non-unitary theory, you'll have a finite number of these primaries.
Yes, if you remember, our discussion of non-unitary minimal models had finite number of primaries for PP prime.
Oh, yes, yes.
Okay, so minimality and unitarity were related but distinct. We got minimality without demanding unitarity, and then there was a special condition on minimality that gave us unitarity. Okay, so what we will do is identify this BRST operator, okay, and we will study its cohomology. Now, even though the Hilbert space is infinite dimensional, this cohomology will be finite dimensional in the sense of representations. Moreover, and restricting to the cohomology of that BRST operator will give us the minimal model. That is how it's going to work. Okay? Moreover, since whenever we're studying a theory with a BRST operator, we can find different equivalent representations of the same operator. Okay? I give you one representation, you add q of that representation plus q times something, q BRST times something. It'll generate all the same correlation functions. These are just different ways of writing the same operator. Okay? And we're going to see, we will, of course, because we have the structure of BRST, we will have the structure of the BRST symmetry. The same thing will happen here. So what we're going to see, and this is going to be partly the answer to your question, what we're going to see is that we're going to have many different representations of the same operator. The interesting thing about our BRST operator is that it will not carry zero momentum charge. Okay, will not carry zero alpha. It will carry a particular value of alpha. So we will do a detailed BRST analysis, but after we've seen, we're going to do like last time. We're going to explain how things are working and then go into the technicalities after that. Just because I don't want you to get lost in the technicalities are very technical. Okay, so let's see how things are working and then we'll have a lecture on the technicalities. Okay? Please.
So, like, can't we also do, like, there are these two operators having the same dimension?
Yes.
Let's just orbifold with that identification.
Yeah, that will not be enough. You see, as you will see already in this lecture, we will need not just these two representations, but we will need to work with the whole infinite class of representations that we get by acting with BRST. You will see. Yeah. Okay. Yeah. So it's just the equivalence of these two is not enough. Okay. Okay. Now, so what I'm going to do is this lecture I will just very roughly motivate some of these equivalences, and we'll work with them. After we start seeing the structure, either next lecture or the one after that, wherever. Once we finish the general study of this thing, we will come back to a detailed description of this BRST quantization that will explain the technicalities.
Just
Go on.
follow up what you are saying. So you are saying that we'll have infinite number of these, let's say, primaries, but then you will classify them into finite number of equivalence classes.
Exactly. Exactly. Okay? And all of these, then you work with some representation or the other. Okay? You're going to get, you choose the thing that works for you. Okay? Now, that something like this, and there's one element I haven't alluded to. You know, there's this BRST plus there's something else. Is very similar to those who are familiar with string theory with the picture changing operator. Okay. If you remember, I don't know how many of you, none of you were in my string theory class, but I don't know how many of you remember this. But when we are computing correlation functions on the world sheet of the string in the RNS formalism, including the superstring, we're forced to add these picture changing operators. Does anyone know that? If it's not familiar, I won't make this comment. Okay, I'll just make this comment for the record, for the camera. Okay, so, these picture changing operators are totally crucial. Let me just remind. Anyway, when we work with vertex operators in the RNS formalism for the superstring, we bosonize the bosonic beta gamma ghosts. We get an equivalent representation for them, and similarly for the BC ghosts. And in this representation, you only get non-zero correlation functions when the total charge, the total momentum charge of this effective new boson is 0. Okay? But this is sometimes called ghost number conservation. Okay? But if you work with any particular representation of the vertex operators, okay, you add up the charges and in general it's not zero. So you might fool yourself into thinking that S matrices of 4 gravitons are zero. The way it works is that there is this picture changing operator that allows you to change from one picture to the other. This has a tight interplay with BRST symmetry, okay, and take you from one representation to another, roughly because possible because there's this BRST correlation. And these different representations have different momentum charges. Okay, and you choose the pictures, so it's always possible to choose pictures so that the charges add up to zero. And you make that choice, and then compute the correlation functions.
Shouldn't it have been invariant under adding?
Shouldn't it have been invariant under adding? No, I mean, yeah, there is this, you get something that would have been zero. Yeah, the rules go that you choose the picture to make it non-zero. Now, why was it just, you're saying it should have, if it was 0 and 1, why isn't it 0? Yeah, it's, from some deeper level, there is probably a reason for adding these picture changing operators, the number of picture changing operators with each of these operators. But the way we usually do it in string theory is just add as many as you want.
Zero modes when we add for B and C.
It's related to zero modes of the beta gamma system. Okay, there's a particular operator you can make and argue that, insert in the correlation function. Then you can argue that the correlation function doesn't depend on where you put it. So you can put it anywhere. There's this whole story. This allows you to go from one picture to another. Okay, something similar is going to happen here. This is why I brought it up. Okay, for now, we will close our skepticism, accept various funny rules, okay, and then come back within 2 or 3 lectures to try to justify the rules more carefully. Is this okay? Good. So, let's try to develop some of these funny rules. The first thing that you might be worried about is this. Suppose you took a fundamentalist point of view. You take some operator and say, this is my operator. Okay? This theory looks like it has no chance of making sense. Because if you computed V alpha of x, V alpha of z, V alpha of 0. Oh, I should have reminded you. We also had the charge conservation rule, which is in a correlation function, V alpha 1, V alpha n. Sum over alpha n was equal to, where did it go? 2 alpha naught. It was 2 alpha naught. You remember we derived this last time from the word identity from translations, right? Okay, so now if we apply this formula on this operator here, we will find that it would appear that V alpha, that this correlation function is equal to 0 unless 2 alpha is equal to 2 alpha naught. Okay, so it would appear that the only operator in this theory that has non-zero 2-point function, hence can be identified with a reasonable operator in our minimal model, okay, is the V alpha with alpha naught itself. Okay, this is how it might appear. So then, if this is a game of trying to be fundamentalist, say, in the sense that each vertex operator is its own operator, and not allow these equivalences that I'm going to tell you about, then we would conclude that the theory was pretty empty. Then one primary, the analog of the identity in the free boson theory. Okay? Notice, however, and this goes along the lines of the questions you were asking, Rajat. Notice, however, that from this relation on dimensions, wherever this was, we notice that h of 2 alpha naught minus alpha, which is equal to 2 alpha naught minus alpha, the whole thing square. Maybe it's better to write this. Let's write this also as equal to alpha minus alpha naught, the whole thing square, minus alpha naught square. Okay. Now it's clear from this representation that h of 2 alpha naught minus alpha is equal to h of alpha, because 2 alpha naught minus alpha gives you alpha naught minus alpha, the whole thing square. Okay, so we notice that this thing is equal to h of alpha. Okay, so if there was some reason to allow ourselves to use many different representations of the same operator, very much like picture changing. Okay, and one of the different representations we could use for this operator was this guy, v of 2 alpha naught minus alpha. Then that completely takes away the constraint on 2-point functions, because v of 2 alpha naught minus alpha of z, v of alpha of 0. This always obeys charge conservation, because the sum of these two guys is always alpha. Okay, so this will be part of our rule. Part of our rule is that we can use either v alpha or v2 alpha naught minus alpha as a different representation of the same operator, and indeed we'll use one or the other, or one or more complicated things, as we will describe, in order to get non-zero correlation functions, very much like picture changing. Okay, again, the logic for this we will develop as we go along. The formal justifications we will develop, but this is part of the rule. Okay, is this clear? Okay. Now, the next thing we do is the following. You see, suppose we had 2-point functions. You remember that the fusion rules of operators in a minimal model allowed a wide range of possibilities. Remember, if you took R1 S1 and R2 S2, we got everything from R1 minus R2 plus 1 up to R1 plus R2 minus 1, and similarly with the S's. So we want to generate a similar fusion rule, a similar kind of fusion rule this way. So something where you take two guys and you get many possibilities. Okay? But even this extra leeway of allowing ourselves to use alpha or 2 alpha naught minus alpha doesn't help very much then. Because suppose I have two operators, let's say v alpha 1, v alpha 2, and I take the fusion of these two, then I could get, maybe 2 alpha naught plus alpha 1 plus alpha 2, and maybe 3 more possibilities, depending on whether I flipped alpha 1 or alpha 2 with 2 alpha naught minus alpha 1 and 2 alpha naught minus alpha 2.
So total 4.
Total 4. But you remember that in general our fusion rules produce many things. Right? If we started with R1 S1, went to R2 S2, we got roughly R1 plus R2 minus R. Let's say R2 is smaller than R1. We got roughly R2 or maybe 2R2. Such possibilities. Something that grew to be very, very large when these R's were large. Won't be exhausted with 4 possibilities. Okay? So we need further relaxation of our rules in order to be able to get fusion rules that look anything like that of the minimal model.
So we are now trying to get minimal model out.
Yeah, this is our goal. This is why we're studying these theories. We're going to tune our alpha, we'll give you some logic for that, alpha naught, so as to meet the central charge of the minimal model. And then we will hope to try to construct the correlation functions of the minimal model constructively. Okay? Our primaries are going to be various v alphas. Okay? That's how we're going to try to work. Our primaries will be various v alphas. Okay? But as we've just seen, this rule of assigning a particular v alpha to a primary cannot work. even with this twofold degeneracy, cannot work. We need something more. Go on.
Maybe I missed something, but apart from these operators,
Yes.
I mean, del X kind of operators are not parameters.
There are no other primers. No other primers. Just in the free boson, del x and e to the pi kx was a full set of primaries.
But no modification to del X also makes it a primary.
No. Yeah, you know, del x was roughly speaking.
That was momentum conserving current, but here it's not conserved. So
Yeah.
I can say
Yeah. Okay, excellent. So these are going to be our primary operators. And so we need further relaxation of the rules. So we're going to try to develop something like this picture changing operator. So, you know, some further redundancy that will allow us to change charges and declare that these things are, you know, some identity. But whatever redundancy we manufacture, if we manufacture some redundancy, we have to do so in a way that doesn't change the conformal transformation properties of our things. And it looks like we're stuck, right? Because if I give you a particular scaling dimension and I look at my V alphas, it looks like I've just done everything I can. These are the two operators with the same. You just look at that. That's a quadratic equation. It has two solutions. So it looks like we don't have too many more possibilities. Okay? But there actually is another possibility, which is a very clever one. Okay? And the way we're going to, the way this possibility works is that it generates new representations by doing something non-local, as I'm now going to describe. Okay. What we're going to do is to look for V alphas that have the property that their scaling dimension is 1. Okay, so that these V alphas would behave like conserved currents. Okay, so suppose I want V alpha such that V alpha such that, you know, alpha such that V alpha is 1. I have to do alpha squared minus 2 alpha naught is equal to 1. So alpha squared minus 2 alpha naught minus 1 is equal to 0. And therefore alpha is equal to 2 alpha, let's say alpha naught plus minus alpha naught squared plus 1. Okay, looks familiar? These were alpha plus minus. Okay, so there's a special role for the weights alpha plus minus that played such a big role in our study of the minimal models. You remember all our weights of operators were r times alpha plus s times alpha minus, right? You remember that? Okay, so these operators, from this point of view of this linear dilettante theory, these values of alpha plus and minus show up as being special in the following way. They're those values of alpha for which the scaling dimension of the vertex operator is 1. Is this clear? Why is that important? This is important for the following reason. Okay, this is important for the following reason. It's important because integral dz, so now let's call these guys v plus and v minus. This is, so v plus is, I'll just call it v alpha plus and v alpha minus. Okay? These guys have a scaling dimension 1. Therefore, integral alpha plus minus has scaling dimension 0 and indeed is a conserved charge. Clear? As always. But what's important about these V alpha pluses, V alpha plus, V alpha minuses, is that they don't carry 0 x momentum. In fact, they carry x momentum, phi momentum, alpha plus and alpha minus. Okay? So, what? V alpha plus and V alpha minus don't carry zero momentum. Momentum is this translation charge, the thing that was conserved, had to be conserved after this 2 alpha naught. Right? I mean, by definition, they carry momentum, alpha plus and alpha minus. It's e to the power I alpha plus, square root 2 alpha plus times phi, and alpha minus times phi. Clear?
So why it's 0?
What?
Why it's 0?
It's not 0. Yeah. Okay, you know, I brought this up because usually the kind of conserved charges we deal with in, let's say in the free boson, there would be a conserved charge like del x. Okay, oftentimes the conserved charges we deal with carry that charge 0. They take a sector with a particular momentum and map it to the same momentum. Actually, another example of a conserved charge that doesn't carry 0 is we've already studied. When we looked at this SU2 current algebra that was generated on the self-dual, at the self-dual radius. There we had e to the power I x and e to the power minus I x. It's a little bit like that. Okay? But the most familiar values of this carry charge 0, this one does not. Now, suppose I've got an operator here. I've got some V alpha. Okay? And I act on it with Q plus minus, by which I mean I take this operator, okay, and I go round this V alpha with this contour with this inserted operator. Okay? Now, because this guy carries 0 conformal charge, this was conformally invariant operation. Okay? You don't change the conformal weight of the effective operator you get by doing this action. Okay? This is something that one can, check very explicitly. Let's check it. What we want to do is to, let's say that what we want to do is to compute Lm, the action of Lm on this guy, right? So suppose we want to calculate the action of Lm on this composite guy. Okay? So in order to do that, what we would do is we'll remind ourselves the following. We'll remind ourselves that T is expanded as Lm by z to the power m plus 2. Okay? And so the action of Lm on this guy would be Lm on this Q plus on V alpha. Okay? Where this is integral z to the power m plus 1 T of z and then the 2 pi I. And this guy is integral V plus minus of z dz. Let's call this z and let's call this w. Okay? Now, what we do is take this, imagine that we do this integral last. Okay? So we have this integral, that this is at some point, this is at some other point. This being v plus minus. Clear? Okay? So what we do is we deform this contour into a contour that circles this point plus a contour that circles this cross. The contour that circles this point will give us the action of Lm on the original operator. Okay? and therefore will obey the Virasoro, will give us what we get from Virasoro. Okay? The contour that circles this cross, let's look at that guy. That's the potential for something new. Right? That's the potential for something that will change the action of this guy. Okay? So, this contour was z to the power m plus 1. I'm not writing the 2 pi I. T of z v alpha plus minus of w. And then we do the contour. Okay? So what we want to do is to pick out the pole in the OP of T of z with v as we do this. But this guy here was an operator of dimension 1. Okay? So we get z to the power m plus 1 times 2v of w by z minus w, sorry, just v of w by z minus w, the whole thing squared because dimension 1. Okay. Plus del v of w by z minus w. Okay. And now we get what? Yeah. So then this becomes, let's see. This becomes, so now we have to Taylor expand this. So we get m plus 1 w to the power m v of w plus del v of w. This whole thing as what is left over when we do this thing. Is this okay? W to the power w to the power m plus 1. Right? Okay. And now we have this guy integrated. M plus 1 w to the power m v of w plus w to the power m plus 1 del v of w integrated over this contour. Okay, now we will take this and integrate it by parts. Okay, so this becomes integral of del of w to the power m plus 1 v of w, and then minus 0 because the other term cancels this term. Minus m plus 1 minus m plus 1 w to the power m. Okay, and now since this was a closed contour, this was an integral of a total derivative around this closed contour, this is 0. I just told you something obvious. You know, I acted with this conserved charge, this dimension 0 conformal operation, and it's not changed the weight. It's not changed the weight of this primary. Okay, I've not gone through the whole argument, but this is the key point in the argument, that when you take this around to this other point, you generate nothing.
What about on this center point?
On the center point, it acts like it acts.
It acts trivially.
Not trivially.
It will give the weight.
It gives how it should act.
Yeah, it gives the weight, but there's another integral involving w integral.
Yes, and then yeah. So then it gives you the action of that and w acting on those. You see, so the kind of thing that you're going to get is, let's say you get, okay, you see, what we want to do is to show that this contour has the same contour acting on state, has the same properties as state itself. So let's say that we get, some, acting with this LM. LM gives us on the original primary V alpha of Z. Let's say that there is a term that gives us Z's, that gives us del squared V, for instance.
V of 0.
V of,
Sorry.
okay, let's call it some V of alpha. It's a third point, wherever it was located. Okay? Now, we will get del squared of that, but then on top of that, we have this guy acting. W acting. Now, this is still an operator that is labeled by where V acts. Do you understand? So what we're going to get is some new, let's say that this operator Q plus on V of alpha, it was not labeled by where the Q plus contour was, because that was conserved. So this object here, V alpha, give me another UVW, U. Okay, so there's another complex number. Okay, so we had Q plus acting on V, which was located at U. This is some effective operator which is labeled just by U. Okay, so you get some derivatives on U, but that gives you derivatives of Q plus acting on U. So it's exactly what you should get. Are you understanding? Okay, so what these things will do will give you whatever it gives you, that will be accompanied by this other contour around it. And that is what you should get for this new operation.
Basically, Q plus commutes with L.
Yeah, basically Q plus commutes with L. That's what I wanted to say. Exactly. Maybe I should just have said that. I should not have put the operator at all. This Q plus commutes with L, and then once you've done that, it's clear, right? Okay, maybe I should have just stated that. Okay, that's what we've proved, really, that you can take this contour. Is it? Okay? Because of this now, if you do this operation, you're generating some new object. Okay? You're generating some new object that will have the same conformal weights as the object that you started with. Okay, now let us see. We'll come back at some point to examine this a little more closely, to examine microscopically what this new object does. But let's move on. Let us see how much this helps us. You see, given a V alpha, I can act on it with Q plus to the power m and Q minus to the power n. I can circle it with mq pluses, nq minuses. Okay? This is the kind of operation I can do to get objects that will have the same conformal properties. Is this clear? What is the weight now of this new object? The weight of this new object has alpha, the momentum charge, the translation charge. Alpha has gone to alpha plus m times alpha plus n times alpha minus. Clearly. Okay? Now, suppose therefore, we will be able to find a picture, a choice of representation of our operator that will be able to conserve charge, provided all our charges are conserved up to integer multiples of alpha plus and alpha minus. Because this new operator can be used to absorb away any difference. Okay? actually this plus the other guy, because you want to be able to absorb away with both positive differences and negative differences. And you use this, the other one. If alphas are all very large, you use the 2 alpha naught minus alphas, then they all become very small, to get a negative difference. But anyway, modulo that, if there are integer differences, we can use this picture to absorb away the non-conserved charge. Yes?
You're basically identifying all the operators which are generated.
Yes, this is going to be again any operator that is identified by the action of either this q plus circling an operator or q minus circling an operator any number of times has the same conformal properties, and we are going to allow ourselves to use whatever we are going. What we want to do is to construct correlation functions of primaries in the minimal model. We are going to allow ourselves to use any of these guys, whatever works for us, so as to get a non-zero correlation function. Okay, the justification from that will come from this BRST discussion we'll have later.
But I mean, we had a continuum of operators.
Yes.
And we are still reducing some countable infinite.
Okay, but now look. Suppose these guys, the original alphas, see, how is it going to be that you had that every difference you take, so every sum of alphas that you take is some integer linear combination of alpha plus plus alpha minus? Clearly, only if the original operators were linear combinations of integer linear combinations of alpha plus plus alpha minus. Also, clearly that is a closed thing to do, because we focus on only operators which were integer linear combinations of alpha plus plus alpha minus. When we take products of these, that won't change. Okay, so first thing we do is now focus on that subsector of the theory in which all momenta are integer linear combinations of alpha plus and alpha minus. Focus number one. Yes?
This, when you apply any q plus or q minus on B alpha, it still remains a primary, right? Because you can
Yes.
get L plus inside. And
Yes.
still have negative.
Yes.
And I think the weights also do not change.
Don't change, because all conformal properties are the same.
So then how do you have so many primaries now?
Yeah, it's strange, right? How did you suddenly manufacture so many primaries when it didn't exist? Yeah.
We can exactly compute what this q plus B alpha OP, we can compute OP between these operators between B alphas, right?
Yeah.
We can say maybe it's just proportional to B alpha, then we are not effectively.
No, but we're changing alpha as we see, right? Because alpha adds. Yeah. You see, a point that is important is the following. V alpha, okay, in the neighborhood of another V alpha is not by itself single valued. Okay? So, this point I was planning to bring up only later, but since you've let's remember that. Suppose I take V alpha 1 and V alpha 2. Okay? Suppose I take this V alpha 1 and V alpha 2 of Z and W. I do the OP with this. Okay? I can compute the singularity in this OP. This is going to be, if it was just a free boson, it would be Z minus W to the power alpha 1 times alpha 2. And in general, these things will not be integers. Okay? So this whole operation here, this operation of circling with this V alpha, okay, was not really a legal operation because it was not single value. That's why this operation doesn't really give us a new legal vertex operator. But when we study correlation functions, we will be able to do this circling in a way such that in the whole correlator it's single valued. Yes. So, but let me just finish this. So it's not really like there is a new vertex operator. As you say, the vertex operators are in front of us. But there is a new operation which will generate non-zero correlation functions. Okay? And that operation will depend not just on what happens operator by operator, but on the whole correlation. We'll study an example of this, maybe this class, maybe the next class. It's a very good point and then one that's confusing. Yeah, go on.
When you're integrating this V alpha has like both left moving dimension and.
We're doing chiral.
Only chiral.
We're just looking at the chiral sector of the theory. We can also study the non-chiral sector of the theory, but you remember that all correlation functions are products of holomorphic and anti-holomorphic. So what we're trying to do is to construct all the conformal blocks.
But I was saying that. So initially, the reason we didn't get non-trivial factors when moving around.
Because we had both, and that's not what we're doing now. What we're trying to do is to construct the conformal blocks. You remember how we studied the correlation functions, the 4-point functions, let's say, of the Ising model. We looked just at the holomorphic sector, looked at the correlation functions that we made out of those. Those are the things we're trying to construct. Okay, sorry. So I should have said, it's not that we're going to get the right correlators through this. We're not going to get moduli and variants and so on. This is a method of constructing these conformal blocks. And then we will have to use some other input to try to combine the conformal block with the anti-conformal block in a way that gives you single-valued correlation functions. Okay, but our aim here is just to compute these conformal blocks themselves. Okay, yeah. Okay, yeah. So as Chintan asked, had it been a legal vertex operator by itself, okay, it would have been one of the V alphas. It's not quite that, but it's an object that we can insert into correlation functions provided in the end all contours are made single valued. We will come to that. Okay, so it's a formal object at this point. Had it been something that just gave us another vertex operator, it would have not been much use, because the vertex operators would have been in front of us. We could just use those vertex operators. Right? So it's more than that. Yes?
I don't understand the point. So all those alphas, that alpha plus plus m alpha plus plus n alpha minus, all those alphas are there in the spectrum, right?
Yes.
You have this h alpha as a function of some alpha.
Yes.
So all those alphas are there in the spectrum.
Yes.
So we don't get any new operator as this, right?
We get a new object. This is not quite a new operator because we're doing something illegal. We're taking this contour and evaluating it, even though the object that we were integrating is not single valued. So what exactly we're getting is not clear, because I can move this, rotate a little bit, I'll get something different. So only when I put the whole thing together in a correlation function that what we get will be clear. And in fact, this is why we will get multiple conformal blocks, not one conformal block, as you will see. Had it been that we would have got a specific thing, we would have got an answer. But that's not how it works, right? As you remember, we get RS different conformal blocks for 4-point functions, because there's an order RS differential equation. We will find all of those from this procedure because of these ambiguities. But please go on.
So after the action of this Q plus on V alpha,
yes,
you'll have some different V alpha prime, let's say.
No, we don't get something well defined, because this action of this Q plus was not single valued.
Okay.
It was not a well defined operation by itself.
It's not of the form e to the power I k phi.
It's not of the form anything, because it was not well defined. What you're allowed to do is to take something that's single valued and integrate it around. The fact that this was not single valued tells you it depends not just on where this guy was, but also on where you make the cut in this contour.
So my next question is, why are you assigning this alpha goes to alpha plus m alpha? What is that refined alpha?
What?
That alpha prime, sorry.
It is just the charge of, you see, in the end what we will have is some sort of correlation function. Let's say we want to find a 4-point function of four alphas. We'll have V alpha 1, V alpha 2, V alpha 3, V alpha 4. Okay, we'll have these 4 insertions. Then we will have some number of these Q operators. So we will have V plus of W1, V plus of W2, those associated with alpha 1, those associated with alpha 2, and all of these will be integrated around some contours. In the end, this is what we will be computing. The point is that the thing we will compute will have the same properties, will obey all the word identities for a 4-point function of V alpha 1, V alpha 2, V alpha 3, V alpha 4. We'll have no dependence on what we did with these W's as far as its conformal properties are concerned, as long as these W contours close appropriately. Okay? Now, this whole thing has to be non-zero. So it's only non-zero if this whole thing, its charges add up to 2 alpha naught. That's all we're saying.
You're saying that there's no dependence on V alpha plus.
No, I mean there is dependence only on the choice of contours. We'll have this correlator and we'll have to integrate this guy over some contour. This thing is a conserved charge. So any small deformation of the contour doesn't matter, but there may be inequivalent contours, globally inequivalent contours, which this will depend on. And the various choices of these globally inequivalent contours will give us the various conformal blocks. But under conformal transformations, this object will transform exactly like 4 insertions of V alpha 1 to V alpha 4. Its conformal transformation properties, whichever choice of contour you make, will be that of a 4-point block. That is in the end what we will do. Okay, all this is leading up towards that. Okay, so all that we are trying is to give you an explicit construction of a 4-point function that has all the correct conformal transformation properties of the and not just 4-point n-point function of the primary fields in the minimal model. Is this clear? Now you see that the conservation adds up is in this object. So the n's, it will only conserve provided all the alphas are integer multiples of alpha plus and alpha minus. Is this clear? Okay. As we go on, some of these unsatisfactory things will become clearer as we understand the more mathematical justifications for it. Okay? But let's proceed and see how we're working before let's see what we have to justify before we try to justify. Okay? Clear? Excellent. So now we have at least something to shoot for. The shooting for is we have a logic to restrict to V's of the form R alpha plus S alpha minus. Maybe last time did we do R alpha minus S alpha plus? How? When we studied minimal models. What? R alpha plus? Yeah, that's what I wanted. Okay. So this guy. Okay. So we have some logic to restrict to the to operators of this form. Remember, this is precisely the form of the operators we studied when we studied minimal models. Okay? And we have some rationale, okay, and we have some hope for a procedure for generating the conformal blocks. Okay, the procedure being you put these V's in here, and then you put as many insertions of Q's as you need. You put as many insertions of Q's as you need to conserve charges. It's always possible. Okay, either with the representation alpha or with the representation 2 alpha naught minus alpha. Using one of them, it's always possible. And then you just try to compute this object, okay, which you can do using free field methods. Okay.
What was our motivation of constructing these objects, Q plus?
The motivation was we wanted to construct something that could change the charge conservation without changing the conformal transformation properties. We want to compute a 4-point function which has the conformal transformation properties of 4 primaries in the minimal models. We don't want that to change, otherwise we've not got the answer. But we can't get an answer of that form from this theory, because if we just stick to the V's, because the V's in general don't conserve charges. So we wanted something that would change the charge conservation, but not change the conformal transformation properties.
So you want to bring down the like some of these alpha i's to be not 2 alpha naught but 0, something like that?
No, that I want to be able to work with arbitrary 4 guys and put some insertion such that in the end of the day we will get some being 2 alpha naught. Even 0 wouldn't have helped us, because it's not true that there is a strict charge conservation for 3-point functions, for instance, in minimal models. We don't want any charge conservation. That's an artifact of this representation. It's not true in the minimal models. Clear? Okay? Great. Okay, let's move on. Excellent. So we've almost hit on the structure of the minimal model, but of course there's one thing we've not done. We've not seen why particular values of the central charge are special. Okay? But there's also one thing that we've not accomplished. We've also not accomplished having only a finite number of fields. Because at the moment our V's could be any alphas. Okay? Our V's could be R times alpha plus plus S times alpha minus. And for any choices of those without any periodicity properties.
If there is some periodicity, then we can say that.
Then we will have come near to the minimal models. Right? And then this discussion is very similar to a discussion we had, 5 lectures ago, 6 lectures ago. Suppose it was the case now let us just suppose it was the case that everything we've said so far is just general, but now suppose it's the case that P prime alpha plus P alpha minus equals 0 for 2 integers P and P prime. Okay, then clearly adding m times P prime to R and m times P to S, okay, does not change anything. Our V which was labeled by R and S, 2 infinite sets of integers. Okay? If this was the case, it would now be labeled by 1 finite thing and 1 infinite set of integers. Is this clear? Okay? Now we want to do better. We want to do that we get labeled by 2 finite ranges of integers. That will come out dynamically. That second cutting down of infinity to finite will come out dynamically. It will come out from a property of structure constants. Okay? This we choose by hand, and then the last good thing comes out automatically. Okay? So if we make this choice that P prime alpha plus P alpha minus, we could have chosen, this is some constraint because alpha plus and alpha minus are functions of alpha naught. This is some constraint on alpha naught. If we make this choice, which is of course also the choice we make when we study minimal models, this is why we're trying. Okay? Already from this point of view, one good thing happens, which is that one of the infinities that you have in the game goes away. The infinities in the labeling of operators. Clear? No, just much simpler. That suppose we took VRS. This object is e to the power I R alpha plus S alpha minus, maybe with some square root 2 times phi. Now suppose we take the two values Rs and the values R plus P prime M
Yeah, I understand that two vertex operators with different momenta
are the same vertex operator.
are the same vertex operators. But you could do one more thing, right? You could act on VRS with
No, yeah, but as we've discussed, that's not exactly the same as getting a new VRS.
okay,
Yeah, so that's a different thing.
Here even the momentum will be same, right?
Yeah, it's just exactly the same operator. Yeah. Okay, excellent. Okay, so we make this choice, and once we make this allows us to find alpha naught in terms of these two objects P and P prime. Let's do that. So we have alpha naught plus square root of 1 plus alpha naught plus minus plus, right? Alpha naught square into P prime plus alpha naught into minus square root of 1 plus alpha naught square into P is equal to 0. Okay. So this allows us to, so let's see. So let's solve for alpha naught. So we can do P prime minus P into alpha naught is equal to P, P prime plus P. P prime plus P into alpha naught is equal to P minus P prime into square root of 1 minus 1 plus alpha naught square. Okay, and then just square and solve. Right? So P prime plus P over P minus P prime, the whole thing square. Alpha naught squared is equal to 1 plus alpha naught square. Okay, go ahead, solve this, plug it back into the central charge. Okay, and you will get, let me, yeah, maybe there's a simpler way to, anyway, probably a simpler way.
We'll get the same formula
As before, yeah. And in particular, you'll get alpha plus is equal to square root of P divided by P prime. Alpha minus is equal to minus square root of P prime by P. And C is equal to 1 minus 6 P minus P prime, thing squared divided by P prime. Okay, so we just recover the old formulas we had for obvious reasons. We're doing the same thing. Okay, in terms, now there's no alpha naught anymore, there's a P and P prime. Okay, great. Okay, now the claim is that with this formalism, if we now evaluate the correlation functions that you are interested in, okay, with this formalism, we now evaluate the correlation functions that you are interested in, you will recover all the conformal blocks. You will recover all the conformal blocks of the corresponding, all the conformal blocks of the corresponding minimal modulus. Okay? I want to first show you an example of how this works. Okay? Before we come back to justifying all this more clearly. Okay, but first you see the claim is a very interesting one. First you should appreciate that. We had these extremely complicated looking interacting conformal field theories. It looked like they had nothing to do with free field theories. For instance, in the Landau-Ginzburg description of the unitary minimal models, these theories are as difficult from that point of view as studying Wilson-Fisher theory in 3 dimensions. You know, del phi, the whole thing squared plus phi to the 6. How do you study it? It's a bit complicated quantum field theory, right? It's not free. Okay? The claim is that we can more or less solve, not exactly solve, we can more or less solve because we can compute all the conformal blocks. Then we have to do a little more to put them together. But we can more or less solve for these theories by doing a calculation in a free theory. Because this theory here is a free theory. All correlation functions can be computed by Wick contractions. Okay? So it's actually, if you think about it, an amazing claim. Because it gives you a constructive trivialization. Maybe not trivialization, maybe is the wrong word. But a constructive way of solving all of these theories. Okay? So I want to emphasize this, that the claim is a remarkable one. Okay? I hope you've understood at least what the claim is, and we will come back either next lecture or lecture after that to justify that claim better and better.
But this theory like comes back to minimal models only for certain values of alpha.
Yes.
It's restricted in that sense.
It's restricted in that sense, but it's not restricted from the point of view of the minimal models. Every minimal model you can solve this.
Yeah, every minimal model you can solve, but here you cannot solve every.
Well, here in this theory, it was a free theory. So we can solve this theory as much as we want. What we want to do is relate the results of computations in this free theory to answers we would get in a non-free theory. Okay? It's true that if you gave me some conformal field theory that was not a minimal model, I can't solve it using this technique, so at least I don't know how. But at least for the minimal models, we can. Okay? So the point is not to solve this theory is trivial. The point is to use what we can do in this theory to solve the minimal models, which are not trivial. Is this clear? Anything you want to compute in this theory, you can compute. It's free theory. Okay? Great. Okay. So now to show you how all of this is working, let's take a special case. Let us suppose we are interested in a correlation function which is phi r1 s1, phi r2 s2, phi r3 s3, and phi 2 1 in some minimal model. V, maybe I should call it V. Let's invent the following notation. Let's call V r1 s1 is equal to V alpha with alpha equals r1 alpha plus s1 alpha minus. Okay, so I'll just use the notation of V. So what have I done? I'm looking at the most general 4-point function, almost the most general 4-point function I've not even told you which minimal model, P prime left free, except that I demanded one of the operators be phi 2 1. Now why have I demanded this? I've demanded this because we already know something about the answer to this. You see, about 3 lectures or 4 lectures ago, we studied the differential operator that we got from having a phi 2 1 in a correlation function. In that lecture, I worded it as, let's study the correlator of 4 phi 2 1s in a Ising model. But actually, all we used was a null state condition for phi 2 1. Okay? And we didn't use anything else about what the other operators were. So some generalization of what we discussed there applies to this discussion. And the key point was that we will get a second order differential equation. Okay? So this correlation function, no matter which minimal model we study it, will be subject to a second order differential equation, and so should have 2 conformal blocks. You remember the conformal blocks for hypergeometric functions, right? We should expect two hypergeometric. We should expect that differential equation would be a hypergeometric differential equation and give you two solutions to two conformal blocks. But here we're not using any differential equations in this way. We're just constructing. So somehow our construction should land us on these two hypergeometric functions. How is that going to work? That's what I want to explain. Okay? So, okay. Now, we could try a more complicated discussion, but I'm going to further restrict, put one further restriction on this R1, R2, R3, S1, S2, S3 to make the discussion as simple as possible. What I want to do is to work in a situation where I can get away with having just one of these q plus q minus operators. Okay? The point of this discussion is to illustrate the role of these q plus q minuses, the contours and all of that. Okay? So, we can do that if we do the following. Let us choose R1 plus R2 plus R3 minus R4. Plus R4 equals 4. Sorry, just plus, sorry. Well, okay. Well, I want to be in a situation where the neutrality condition is satisfied if we have one q plus operation. Let me first do this R2 S2 R3 3S3 and R4 S4. Okay, I'll specialize in a moment to R2 S2 being 2, 1. But let me first work in general and choose a situation such that R1 plus R2 plus R3 plus R4 equals 4 and S1 plus S2 plus S3 plus S4 equals 2. Okay. Now, let's check that this neutrality condition is satisfied.
If the sums of R and S are same, then also it is satisfied.
What?
The sums of R and S are same. Because alpha plus and alpha minus when you add, you get 1.
Right. So we get alpha plus plus alpha minus is equal to 2 alpha naught. No, but I'm sorry. And then there is a q plus. I want one q plus here. You know, that's why it's going to change that's why it's going to change, as you say. So what we need is that this thing should add up to 2 alpha naught, which means that the sums of the r's should add up to 1. Right? Because it should be that sum over, so it should be that R1 plus R2 plus R3 plus R4 plus whatever we get with the Q, which came with 1 alpha plus. So plus 1 is equal to, strange. No, but let's get the absolute number. It should be equal to 2 alpha naught, which should have been just equal to 1, right? Sorry.
You could also use this 2 alpha naught minus
Yeah, maybe that's what they've done. Sorry, just what? There's some typo. We'll just work it out ourselves. This is what we would get, right? We have R1 plus R2 plus R3 plus R4 is equal to 1, and we would have S1 plus S2 plus S3 plus S4 is equal to 1. That's what we would get for our correlation. I think they've just made a mistake in the book, so let's move on. Okay, now suppose we choose R comma S. R comma S to be 2 comma 1. Okay. Let me just say it. Okay, so we choose R comma S to be 2 comma 1, plug this in, and we choose the sum of the remaining R3s to satisfy this equation. That's all that's important. Okay, so we choose the sum of the remaining R3s to satisfy this equation. We choose the sum of the remaining S's to satisfy this. I'm not agreeing with the equation they get in the book, but it's got an extra variable also, so it's clearly wrong. It's like a dimensionally inconsistent equation. So fine. So whatever you get. You get the sum of these R's to be whatever you want that will satisfy this charge conservation, and the sum of the S's to be whatever you want so that satisfy charge conservation. Now, what we're going to do is to construct the correlation function that we have here. Okay, what we're going to do is to construct this correlation function in the following way. What's really going to be important is this. What we will do is to set these 3 guys, the guys at 1, 3, and 4, to be at 0, 1, and infinity. Okay, so there will be 2 guys that we've not set to special places. The 2 guys are the one at Z, which is what we're interested in. That's our V2 comma 1. That will be located at Z. But then we will also have our this Q, which is contour integrated at some W. Okay, so in the end what we're going to get is some correlation function which will depend on 2 things, Z and W. Is this clear? What we will do, but probably, certainly next class, is to compute the Wick contractions that give us this correlation function. Okay? And in doing that, we will get some function of Z and W that then has to be integrated over W. Well, now, this function that we get as a function of W will have many cuts. So we will have to choose a contour for this integral over W that makes this thing single valued. And we will find that there are 2 inequivalent choices of such contours. Okay? So in the end what we get is an answer involving 2 integrals. That finally in the integrals we will be able to do by Cauchy's theorem, going over some discontinuities. So it will be an integral from one of them will be an integral from 0 to 1, and the other one will be an integral 0 to Z, and another one from Z to infinity. And these will be 2 integral representations of hypergeometric functions, both of which satisfy the same differential equation. So the fact that we get these 2 inequivalent contours for W will be related to the fact that we get these 2 different hypergeometric functions. Okay, let's do that next time. Okay, so that's where we're going. Okay, so we'll study this correlation function next time.
Right, 2 equivalent contours.
Inequivalent.
Yeah, 2 equivalent contours, you mean the number of bindings around.
The contours that cannot be shrunk to each other. You see, topologically inequivalent. Yeah.